Hopefully there won't be a fire alarm today. We're going to do minimax theory today. I got some references there for you in the introduction. Especially I want to mention the book there by Sibikoff is one of the best books I think about doing minimax theory. So if you have interest in this, want to see more stuff on it, I would recommend looking at that book. As usual, it's a Springer book, so it's free if you're on campus, the PDF at least. So what is the problem we're trying to solve here? Do I have to start locking the door again? I have to resort to that? Well, that one says 129. I guess my phone says 131. I don't know what the... And what does yours say? All right, so I guess the AT&T does not have a reliable timekeeping mechanism or something like that. You'd think they would all be perfectly synchronized. All right. So this, I think, when it comes to theory, this is an extremely important subject. And let's say what it is we're trying to do. You know, we have some data, and we're trying to estimate something. Maybe it's a classifier. Maybe it's a point estimator. Maybe it's a density estimator. Maybe it's something very general. We'll call it theta of p. It depends on the unknown distribution. And remember what the minimax risk is we're going to, for the moment, assume that p is in some set of distributions p. This could be a parametric family. This could be a non-parametric family. This could be very general. And the quantity we're interested in is the minimax risk, which is the inf over every possible estimator, the sup over all distributions in P of the expected value of some, let's say, some distance or some loss between theta hat and theta P. All right, so we're going to look at the distance between theta hat and the truth. We're going to look at the worst expected distance and try to minimize that over all estimators. So just so we have a simple example in mind, if you think about the model, let's think of a parametric model, all the normals, and let's think of squared error loss, then this would be the inf over all theta hat of the sup over all theta, the expected value. That's what we did in 705. And what is the minimax estimator in that case? Hopefully, what's that? Sample mean, thank you. In that case, we knew that we could compute the minimax risk, the minimax estimator. It was just the mean. That was a simple problem. But what we want to do is be able to do this now more generally for things like non-parametric regression, classification, and so on. The simple methods we used there don't work. So what we did there, remember, was we just computed any Bayes estimator. And then we checked its risk function. And if the risk function was constant, then we had got the minimax estimator. But that's a strategy that works pretty good for parametric problems, but we want to be able to do non-parametric problems. So we need a different strategy for this. And there's kind of a generic strategy that we'll talk about. But let me first spend a few minutes saying why we should even care about this. Okay, why do we care about minimax risk and things like that? Okay, so it's not the case that I'm going to say, I think I'm going to work on classification. Let me write down a bunch of conditions for my distribution and define P. Let me now work out the minimax risk, and now let me find an estimator that achieves that minimax risk. That's not the point of minimax estimation. It's not an immediately practical thing that just leads us to solve a problem in a certain way. It's addressing a more generic, or I should say a more abstract problem, which is how difficult is a given problem? If I'm trying to do some sort of machine learning or statistics problem, I want to know how do I measure the difficulty of the problem? So this is just like for those of you in CS, you know, you talk about things being in P or NP or different hardness classes. It's as hard as the planted clique problem or whatever you're, however you're measuring things. Being able to measure the difficulty of a computing problem is just sort of a theoretically useful thing. So you know these are hard problems, these are easier problems, and so on. It gives you insight. That's the same thing with minimax estimation. Figuring out the minimax risk is just a way of quantifying, oh, this is a very difficult problem, or this is an easy problem, and so on. And usually we don't know this number Rn exactly. In some cases we do. Usually we just know that it's going to 0, hopefully. And the best we might hope for is to know the rate. What rate is this going to 0? Is it 1 over n, 1 over n to the 4/5? The rate that we've seen a lot is something like this in many non-parametric problems, where you see how beta is usually some measure of smoothness and d is the dimension. So what we want to see is, where does that come from? How do we compute that? Okay, and so that's our goal. And really I want to talk about not so much the detailed calculations in every case, but the strategy that's typically used for all of these problems. There's a couple of tricks that get used 99% of the time for doing these things. There's two quantities that are going to come up a lot. One of them we've seen quite a bit. The Kullback-Leibler distance between two distributions P and Q, which I'll express it in terms of their densities. We've seen this many times, is the integral of P log P over Q. That's going to turn out to come up in some cases. Another distance that comes up a lot in these calculations, I'm not sure if we've looked at it before or not, is the total variation distance. The total variation distance between two probability distributions, P and Q, is very simple. It's just P of A minus Q of A, and then you take the sup over all events. So that's some distance between probability distributions. It turns out you can rewrite that in another way, which is sometimes very helpful, which we'll use. It's a half times the integral of the absolute distance between the densities. Okay, that might not be obvious. If you want to convince yourself that's true, think about P and Q and consider, among all the sets, consider the special set A equal to P bigger than Q. That turns out to be the worst case when you take this sup. And it's a good exercise to go away with that clue. You can prove to yourself that these two things are the same. For now, though, you can just take that for granted. And in fact, I believe I put in the appendix, there's many, many other distances between distributions. And in the appendix, I've listed a whole bunch of them, and also what are the relationships? Which ones are less than which ones? When is this one less than this one squared, and so on? Nothing that you'd ever want to memorize, but it is handy to have a reference for these facts about these different distances. So I've kind of summarized a lot of the key facts for you in the appendix. That's just something so you can look it up if you need to. But these two in particular turn out to come up quite a bit, so we'll be referencing these. Okay, so the question is, how do we compute this guy in general? So first of all, the strategy gets broken down into two things. Almost always, you break the job into two pieces, finding an upper bound and a lower bound. And then, if the upper bound and the lower bound both go to 0 at the same rate, like let's suppose you find out that the upper bound and the lower bound both behave like 1 over n to the 4/5, then you've at least shown that the minimax rate is 1 over n to the 4/5. They might not agree in the constants, but at least you get the rate correct. Why break it into these two pieces? It just makes the job easier. Getting an upper bound is easy. Pick any estimator. Right? If I take any estimator, and if I look at its maximum risk, then the minimax risk, which is the minimum over all estimators, is certainly less than the risk of that estimator, of any particular estimator. So that's less than the sup over P of all right, let's see if something very important. All right, I got that under control. Okay, so what we do is we pick an arbitrary estimator, stick it in here, compute its maximum risk. By definition, the minimax risk has to be less than that, so that gives us an upper bound. Now, obviously, if I pick a bad estimator, I'm going to get a bad upper bound. It's not going to match the lower bound. So there's some craft here, or some art into choosing an estimator, and you might have to try different estimators. Oftentimes, though, it turns out we've started with an estimator, and we think it's minimax. So we already have this, and we're just really trying to find the lower bound and see if it matches. But we'll see in an example that how to do this. So that's the upper bound, and it may take some trial and error there. The lower bound involves a certain strategy, which is very revealing, I think, about how to think about the difficulty of statistical problems. So here's the strategy. And after this, it's kind of all calculation in some sense. So the strategy is as follows. This class of distributions, script P, could be a very general class of distributions. It could be, let's say, all densities with bounded second derivative or something like that, or all classifiers of a certain form. It could be a very large class. So what we're going to do is we're going to pick a finite set of distributions. Which is contained in script P. And this is going to simplify things greatly. And notice that if we look at our risk, because this soup is over the whole set, and that's going to be bigger than the maximum over a smaller set, that's automatically bigger than the inf and then the maximum of pj and m of the expected value of theta hat and theta j. Theta j here just means theta of pj. So we automatically get a lower bound. If I take this set of distributions, script P, and if I just pick out some finite set of distributions and just solve the problem over this finite set, then I automatically get a lower bound. I'm looking for a lower bound. So here's a lower bound. I'm not sure how to solve this problem yet, but it certainly is easier than solving this problem, right? Because I've reduced it to a finite set. So that's the first reduction. We're going to do a series of reductions here to easier and easier problems. Next, I'm not just going to pick these any old way. Okay, I'm going to make sure that the distance between each of these in terms of this quantity is at least some constant. So let's let, I think I called it S here, yeah, S be the minimum distance. So let's think of this, as some parameter. This is some distribution in here, and then there's some parameter attached to this, and the distance between this and this and this and all pairs is always at least some number S. We're going to pick S. That's the closest these things can be. Then let's do, for any estimator, if I do, what's the probability? And I'm going to use S over 2 here. What's the probability that any estimator compared to the truth is bigger than, and I'm going to use S over 2. The reason for the 2 will become clear later. By Markov's inequality, this is less than or equal to 2 over S times the expected value. This is true for any estimator. That gives me a lower bound on this distance. That means that the expected distance between theta hat and theta is bigger than or equal to S over 2 times the probability that This is just Markov's inequality. The goal here was to reduce the expected value into a number times a probability. So I have a further reduction, namely, this is bigger than or equal to, well, the s I can bring up front, so that's s over 2 times the inf over theta hat. The maximum, again, over all of these pj's, times the probability that and then we're going to do one more reduction. The goal here is I'm trying to reduce this lower bound into a somewhat simpler problem. A problem basically of multiple hypothesis testing. But I want to make sure everything I've done so far is clear. All I've done is replace the big set with a smaller set, rewrite the expected value as a number times a probability. And maybe why I put s over 2 there might be a bit mysterious, but you'll see why hopefully in a few minutes. Okay. So now I have that the risk is bounded by this quantity. I'm still going to have to, it looks like this is still going to be a tricky thing to deal with. Now we're going to do one more reduction. I keep calling these reductions because we're trying to make the problem simpler, but at the cost of getting a slightly weaker lower bound. So let me draw that blob over there as if it's a straight line. And so we have this finite set, and so on. Now, I've restricted this calculation to be over this finite set of distributions, but I have no restriction on your estimator. Your estimator could be anything. So what I'm going to do is anytime you give me your estimator, you give me any estimator, let's suppose it's here, theta hat comes here, I'm going to choose the theta that in my finite set which is closest to the one to your estimator. You have an estimator. I'm now going to convert it into an estimator over my finite set. Okay, so what I'm doing is I'm defining, in the notes I called it, phi star, which is just the closest, the argmin over j. Okay, so this is phi star in this case. And so here's a crucial observation, is that this phi star, or theta k, whatever I call it, could be equal to the truth. Because remember, I'm assuming now I'm only going to compute this over the distributions in this finite class. So the truth is one of these guys. Let's say the truth is theta j. True distribution is theta j. It's either going to be equal to it or it's not. Right? But if it's not equal to it, then this phi star has to be pretty far from this because I've spaced these out. Okay, so that is when phi star is not right, when I didn't get, so suppose the true distribution was theta j for the moment. You compute your theta hat. I compute the closest one on the grid. Suppose it's not equal to theta j. Then I'm claiming that, and I'm going to just write k for phi star like I did in the picture, that obviously the closest guy, this phi star, must be pretty far from theta j. Let's just write that out. We know that S so this is the truth for the moment. Let's suppose this generated the distribution. This is the closest guy to your estimator. This is the projection of your estimator onto our finite set. We know that S is less than or equal to this because that was the assumption that every pair of points is at least S apart. Okay. And now I'm just going to do the triangle inequality. This is less than theta j and theta hat plus theta hat and theta k. But we're under the assumption that you've picked the wrong one. That this is further than this. So this is less than or equal to. In other words, the theta hat came closer to the wrong one instead of the right one. So this came out less than this distance. So this is less than, if I replace this with theta j. That's what it means that you chose, your estimator was closer to the wrong guy. So theta j was not the minimizer. This is just 2 times theta j theta hat. So in other words, any time this projected estimator is not equal to the truth, it implies that the distance between theta hat and theta j is bigger than or equal to s over 2. That's where the 2 comes from. Okay, so in other words, the probability that the distance between theta hat and theta j is bigger than or equal to s over 2 this event implies this event. So the probability of this is bigger than or equal to, this implies this. This event is contained in this. So the probability of this is bigger than or equal to the probability of this. That's the probability that phi star is not equal to j. So this is a long-winded way of saying this probability is at least as big as the probability that this projected estimator onto the finite set is wrong. Okay, the probability you're far from theta j is bigger than or equal to the probability that it picks the wrong one out. Okay, but this is just the probability. What is phi star? You can think of phi star, it's a mapping that takes the data and outputs an integer, basically. Right? I give you the data and it picks out one of these n things. It either picks theta 1, theta 2, theta n. That's like a multiple test. Phi is some mapping from the data, the sample space, whatever that is, let's say x to the n, to this finite set. It's like a test or a classifier. You give me some data and I'm going to tell you it came from one of those n things. And this is just a particular one. You gave me an estimator, and that defined a particular guy, phi star. Okay. But that's certainly bigger than or equal to if I minimized this over every possible such function. Minimize the probability your estimator theta hat defined, let's call it a test, a guy that picks one of these out a test. Your estimator defined a test. The probability that your estimator is at least s over 2 away from the truth is bigger than or equal to the probability that your test is wrong, that your test makes an error, that it picks the wrong guy out. The probability that your test makes an error is certainly bigger than or equal to the best test, whatever that is, that minimizes the error. So this was all a long-winded way of saying that this probability is bigger than or equal to this, which I'm going to now insert into here. I can replace this now by the inf over all tests, and the maximum this is the key thing. There was a question.
Yeah, I'm not entirely clear on how we interpret phi.
Well, I don't know if test is the right word, but it picks out, I'm telling you, I have data from a finite number of I say I have some data, I have a data set, it came from one of these. You have to give me a function which picks one of these out. So I'm calling that a test because it's like choosing between n hypotheses. It's like a multiple hypothesis test in some sense, yeah. Sorry?
If
Yeah. Not equal to j. Yes. Thanks.
What is this probability taken over? Is it over the data?
Pj, the jth one. Remember, I've picked a finite set of distributions. I'm doing this computation. This whole computation was done for the jth one. I picked one, an arbitrary one. But that's true for each j. So now I'm saying it's the maximum overall.
And is the probability, are we assuming that the jth distribution is a true distribution and the probability is taken over the data?
Yes. I'm saying fix a j here as the truth and do this. But that was true for any j. Therefore, since that's true, for this by definition, this is computed over probability j. And we just showed that that's bigger than or equal to this. And I lost, oh yeah, there we go, there's the end. How did I get that? I'm assuming theta psi, I'm saying suppose your psi star is not j. So psi star is here. What does that mean? It means that the distance between theta hat and theta k is smaller than the distance between theta hat and theta j. That's why you picked the wrong one. So I'm just saying that's less than that.
What is the phi means here?
Phi are the set of all mappings. So phi lives, so let's call it capital phi. Phi is in here, where any such phi is the mapping that takes out the data and picks out one of the n distributions. So I give you n observations, and you have to say it came from distribution 1, or it came from distribution 2, or it came from distribution 3. It's like call it a classifier or a test, whatever you want to call it. If there was just 2, it's like saying is the null true or the alternative true in some sense.
If you take the input here, so can we say that phi always output j?
No, the phi always outputs a number between 1 to n. All mappings that take the data and output a number between 1 to n. It's a guess at which distribution generated the data. You know, I want to make sure this is clear because this is the whole ball game here. Everything after this is just calculation. But this is the key here is that we started with this thing. We're trying to get a lower bound, and I've reduced it to something which I'm going to claim is a bit easier to compute, which is I arbitrarily picked n distributions in the set. The only requirement is they have some distance, call it s. And we showed, now this is a theorem, that the minimax risk is bigger than or equal to that number over 2 times the worst probability over all, what do they call it, test or a selector or a classifier, what do you want, let's call it a selector. Over all selectors, the probability that you have a mapping which chooses a distribution, what's the probability it makes an error under j, and let's look at the maximum probability. Or if you're used to signal processing, as I'm generating from a source, one of n sources, and you have a data stream, you're trying to guess which source generated the data stream. This is the maximum probability, maximum error probability. This is sort of the key reduction which underlies almost every proof, almost every minimax proof.
So you assume the phi can be any mapping, why it shouldn't be always 0?
Why shouldn't it be 0?
Because you can always map
Well,
it to
let's do an example. I'm going to generate from either a normal 0, 1 and a normal 5, 1. And I'm going to take an observation x. Now you give me a rule for guessing whether it came from P1 or P2 that always has 0 error. You might say, I'm going to guess, here's a rule. I'm going to guess it's from the normal 0, 1. Let's call this P1 and P2. If x is less than 2.5. And it's from P2 if x is bigger than 2.5. That would be an example of a rule. That's certainly not going to have 0 error. I don't think you could come up with a rule that has 0 error. We've just basically changed the problem to finding a discrete estimator instead of an estimator over the whole space, because that's going to be a bit easier to.
How do you actually get the loss inequality? Because actually the inequality you get is just replacing Pj in phi, right? So you can, from the second to last equation, you can replace Pj with like in phi, right?
Well, really, first I should say this is bigger than phi star.
Yeah.
And now I can say that the inf over this is the same as taking the inf over all phi's, because every theta hat defines such a phi.
How do you change the order of the maximum? And,
Yeah, don't worry too much about that. I could have just stopped here, and I would have had this is bigger than or equal to this for phi star. But then notice that taking the inf over all theta hat is the same as taking the inf over all phi stars, because every theta hat generates a phi star.
I think you cannot take the in here because you take it here, so you can.
All right, let's. I mean, it's true, but if it bothers you, you can just stop there. Okay. Yeah. Okay, so I know it's like all the steps are simple here, but I know somehow people always find this a little bit confusing. But intuitively, all I'm saying, it's just like you said. I'm taking the problem of estimating the parameter over the whole space and just saying that's sort of easier than just estimating a discrete parameter. That's really all I'm saying. And then estimating this discrete parameter, since they're all separated, really just amounts to the distance between them times the probability of getting the wrong distribution. That's all we're really saying.
But this phi star is depend on J. This phi star.
No,
is-
you don't know. You didn't know I generated it from PJ. It's a function only of the data, not the distribution.
But you define it to be the minimal distance from J.
No, I didn't. I defined it to be the closest one on the finite set. Yeah. Okay.
Still kind of like think that you have like changed the order of inf max and loss inequality.
Yeah. No, I didn't, because I can say this is equal to the probability, right, of bigger than the probability of phi star. But taking the inf of this over all theta hats is taking the inf over all phi stars. Every theta hat generates a phi. Every theta hat now is in the class of all such estimators.
Yes, like we just replace the loss term by the in phi.
Right.
Is this still right?
That's right.
But in that sense, we have actually like exchanged the max term and the in term.
No, I'm saying that I'm saying first we did this, but these two imps are the same because we're on a finite set. Is everybody happy? I don't want to go on until everyone's comfortable with this. This is the critical reduction. That something which seemed impossible, we've lower bounded by something which hopefully is pretty close. I mean, if this lower bound, if this is too small, we haven't got a good lower bound, right? So hopefully this is close enough. And it's still not obvious how to compute this, because there's still two mysteries. I didn't tell you yet, how do I pick this set? There's a lot of possible choices there. Yeah.
Yeah, so my question was on that, is there like some condition on like how you have to pick M, because
We're going to get there.
random M, then this may not go.
We're going to get there. So you can see there's a trade-off, right? If I make n really big, then the probability of making mistakes is probably going to get high. However, they're going to get closer together, so S is going to get small. Conversely, if I make very few distributions, I can make this big, and I want to get a big lower bound because it's a lower bound. So if I take a few distributions, that's going to make this big, but then it's going to be easy to tell them apart, so this will probably be small. So there's going to be some trade-off here between trying to find a good finite set, and we'll see how to do that. So yeah, the mystery still, Well, there's two mysteries I haven't solved for you yet. How to pick the finite set, but even once we pick it, we still have to, how do we compute this? We still have to compute that. So we have a long way to go, but this is the first major step, was to reduce it to this problem. I don't want to go on until I feel like everybody's comfortable with this, because we still have to continue. Is everybody okay? Sort of? You just stare at that for a while. All right, so how are we going to solve this problem, though? How are we going to choose the distributions, and how are we even going to find this thing? So let's first of all deal with this problem. How do I compute this? Okay, there's many different ways of doing it, but the three major ones are what's called Lecombe's lemma, Fano's inequality, and Sibikoff's inequality. They're all kind of doing the same thing. The one I want to cover in detail is Lecombe's method, because it's very interesting, because it really does reveal the connection between general statistical problems that we're solving, or machine learning problems, and the connection to hypothesis testing. So I'm going to start by solving this problem. How do I compute this? In the special case, when I'm going to choose only 2 points in this space, which often turns out to be enough. So I'm going to do a very special construction here. I'm going to do the simplest one we can think of, which is to only take two guys, P0 and P1. For many problems, that actually suffices. Okay, and so here's theorem 4. This is called Lecombe's theorem. We've heard the name Lecombe many times, which says that the inf this is our general risk, is bigger than or equal. Now I called it S over here. For some reason I started calling it delta in here. This is just inconsistency in my notes. I apologize for that. Delta is the same as S. It's the distance between theta of P0 and again, this could be anything, right? This could be a density function, in which case this is some distance between density functions. It could be a parameter. It might just be the Euclidean distance between the parameters, whatever. And Lecombe's lemma says that this is bigger than or equal to delta over 4 times the following quantity. This is the product density. By this, I just mean that, well, actually, let's just write out completely. P at 0 to x1. Minimum P1 to xn. This is a strange looking quantity. This is called the affinity between the two distributions, taking the minimum. But to make this a little bit clearer, I'm going to make a further lower bound. This is less than or equal to delta over 8 times e to the minus n times the Kullback-Leibler distance between P0 and P1. So this is our first minimax lower bound, and we're going to prove it by, well, basically, we've already proved the first part of the theorem. It just comes down to bounding this quantity when there's two distributions. That's what we're going to prove. We're going to prove that when there's only two distributions, you end up with this quantity, which can further be bounded by this quantity. Okay, but now, before I do that, let's immediately answer the question, how do I choose P0 and P1? The answer is, let's choose any distributions in our class, P0 and P1, such that the Kullback-Leibler distance between them is less than like something of order 1 over n. Let's be specific here, say log 2 over n. So, Okay, in that case, what happens when I plug this in? This becomes like a constant. So in that case, we get that the minimax lower bound is bigger than or equal to. This will become a half, and there's an a here. You now have essentially an algorithm for computing a minimax lower bound. Take any minimax problem you want to solve, pick any two distributions you want, as long as they're this distance apart. So just find two distributions that are about 1 over n apart. Compute the distance of the corresponding parameters, and that's your bound. That's your minimax bound. Intuitively, what's going on is you're picking two distributions, P0 and P1, that are statistically difficult to tell apart. When two distributions have Kullback-Leibler distance about 1 over n apart, then they're very hard to tell apart statistically. It's very hard to test whether the data came from one or the other. And the minimax bound is simply the distance between those two things, divided by 16. And we'll see an example of this when we do, I'm going to show you when we do regression, it's going to correspond to picking one regression and a second regression function that are close together. That's all it is.
So P0 and P1 are like some fixed distributions, right?
Any two distributions you want in your set of distribution.
I'm confused about how the distance between these fixed distributions can depend on the number of data points we have?
Oh, you get for each n to choose different distributions if you want.
Oh.
This is a finite sample result. This is not asymptotic.
What's the distance between parameters?
It's whatever distance you want.
I mean,
Could
is
be-
this the distance between two distributions? Or?
Well, no, don't forget, this is a parameter, which could be a number. Like, it could be a function. So this is whatever metric you've decided to use.
So it's the same over there. It's
Yeah.
also-
This will be clearer when we do an example. We're going to do, in a few minutes, regression, and I'm going to show you where that magic number that we always get comes from. The two distributions are going to correspond to choosing two different regression functions. And again, one of them is just going to be the constant regression function, and the other one is just going to be a constant with a little blip in it. You're going to always pick two functions or two distributions that are pretty close together, that are hard to tell apart. And you're going to pick this big enough, just big enough, so that the KL distance turns out to be about 1 over n. Then we're going to compute whatever distance we're using between these functions, and that divided by 16 is the minimax bound. So we kind of reduced it to a simple thing. But I need to prove this to you first. Why is this bigger than or equal to this? This is the missing piece. So we'll prove that, then we'll do an example, and then it'll all make sense, I promise. All right, so here comes the proof. The first part of the proof is actually just repeating this for two distributions, so we don't need to do that, right? We already know, we've already proved here, let's put this up here. I could have just referred to that. That our minimax risk, because I only have two distributions, it's bigger than or equal to, and I've called it delta over 2. And what is this? There's only two distributions, so it's simply the maximum of, it's the probability, let me try to match the notes here, that it's just the max of these two things. I'm just rewriting what I have up there for two distributions. I'm now saying if I give you two distributions, P0, P1, let's suppose for the moment n is equal to 1, just so I don't have to keep writing the product measure. Okay? Suppose I just give you a single observation, and I tell you it's from P0 or P1, and I'm asking, you give me a rule, psi, which takes the x and outputs 0 or 1. It makes a guess at whether x came from here to here. And what we're interested in is the probability of the maximum probability of a mistake. So let's look at the maximum of the probability of a mistake would mean if P0 generated the data, it would be a mistake to say phi equals to 1. Whereas if P1 generated data, a mistake is phi equals to 0. I just want to compute that maximum error. In fact, let's just compute this for a particular phi. Is everybody with me? Okay. We want to know what is this probability and what is the smallest I can make it over all possible selectors or tests phi. Okay, is this clear? This thing, I called it in the notes. So I'm on page 4 here. I actually just gave this a name here. It's the inf over all phi. The maximum for j can only take two values now, 0 or 1. The probability that we get it wrong. The probability that you guessed the wrong thing. We're now going to bound that. I'm going to show you where that number comes from. Okay. Here we go. Trick number 1. A maximum is always bigger than an average. So we're going to say that's bigger than or equal to the average error probability. The probability under 0 that phi is equal to 1. Over 2. Right? The maximum of 2, is bigger than or equal to the average. But now, let's look at what we have here. You give me any test. I'll call this a test. It's not really a test, but a selector. We'll call it a test. You give me any test. I'm going to compute, what is this? This is the type 1 error. This is the probability you selected phi 1 when the truth was 0, and this is sort of the type 2. It's really the sum of the type 1 and type 2 error. It's like a test, except we're not fixing the alpha level. We're summing the type 1 and type 2 error. So here's a fact that is proved on the next page as a lemma. What do you think, without looking, what would you say if you had a guess? What's the optimal, what phi minimizes the sum of the type 1 and type 2 error, if you had a guess? I give you two densities, and I draw an observation, and I say, which guy generated that? And I'm going to sum up your type 1 and type 2 error, the probability of guessing wrong under either one. Which selection rule do you think minimizes the error, some of the error probabilities? If you just had a guess. Something like the Neyman Pearson test, right? The only difference is we're not fixing alpha. So the optimal test is the Neyman Pearson test, which is simply 1 whenever P0 is bigger than P1, and 0 when P1 of x is bigger than P0. The proof is in lemma 6 on the next page. It's very simple. I'm not going to do it right now. But it just corresponds to you take your test, and you add and subtract the Neyman Pearson test, and you'll see you get the error. You get a positive number. It kind of makes intuitive sense, I hope, right? That when P1 is big, you're going to guess it's from 1. When P0 is big, you're going to guess it's from P0. So this is minimized. This inf occurs at the Neyman Pearson test, what we're calling the Neyman Pearson test. Okay, so this is P0 now of size star equaling 1. We've gotten rid of the inf because we actually know what the inf is. Over 2. Right? The inf over all tests is bigger than or equal to the Neyman Pearson one, because the Neyman Pearson one is the one that minimizes it. You see, there's a very close connection here with hypothesis testing. Okay. Now let's write out what this is. This is a probability statement under P0. So this is simply P0 of x dx on the event that we've chosen wrong. When does the Neyman Pearson test, let me rewrite the Neyman Pearson test. Under P0, to choose wrong means to choose P1. When do we choose P1? When P1 is bigger than P0. So we're integrating over the set. Right? The probability when P0 is the truth that you picked the wrong thing is precisely the integral over this set, because that's the set where the Neyman Pearson test picked P1. And this error probability, when is phi star equal to 0? Phi star is equal to 0 when P0 is bigger than P1. So this is over this set. This is just short for the set of x's such that this is true. Okay. We're almost done. Because on this set, what is P0? It's the minimum. So this is the minimum of P0 and P1 on this set. Same here. P1 is the minimum in this set, so this is the minimum of P0 and P1 on the other set. But that's the minimum, and the minimum over this set and its complement. This is simply equal to the integral of the minimum of P0 of x and P1 of x. And I stated it for product distributions. Everything's the same. You know, when you have n observations, this would just be P of x1, x1, x2, P of x1, x2, the product distribution. I just did it for one observation, so I wouldn't have to write that out. So now we actually have something you could compute. If you give me two densities, you could actually compute this. You just take the two densities. You take the minimum, so that would look like this. And you integrate it. And that's something in a lot of cases you could just compute by brute force. And that's where this came from. This is a very fundamental theorem. This is Lecombe's lemma.
Is this like very similar to when you find the risk for the Bayes estimate?
Yes, it's very similar to, notice when you find the risk for the Bayes estimate, you keep track of which thing is bigger than which thing. Is very similar.
How do you take care of the
How do I take care of it? What do you mean?
do we need to consider that it's actually not because it's actually juxtaposing two parts, right, together.
But in the end, the minimum of these two is just some function. And we just integrate it. It's not a density function anymore. However, most people use this lemma in the second form that I stated here. How did I get from here to here? That's just... So I'm claiming here that this affinity, as it's called, is bigger than or equal to e to the minus n Kullback-Leibler distance. That's a further weakening. Right? We want the bound to be as big as possible, but it's just that this is something we're more familiar with and is often easier to compute. And this is just algebra. This is lemma 7. I'm not going to go through the proof of lemma 7, but it just computes in brute force for you that it's just straightforward calculations using like Jensen's inequality and stuff like this, that this integral is, that it's just a fact that in general, the minimum of two densities is always bigger than or equal to 1/2 times e to the minus the Kullback-Leibler distance. That's just a general fact. That's not, don't think of this as part of the Minimax story. This is just more of a convenience thing, that we're taking a lower bound and we're writing it as something a little bit more familiar that is often easier to compute. Okay, so before we do the example, I know that there's a lot of little tricks that went by there, right? And so I just want to make sure we have the big picture. The big picture is simply that the inf of this, of our risk, in this case we reduced it to, we picked any two distributions we wanted. Any two distributions will give you a lower bound. The trick is to get a good lower bound. And when we reduced it to 2, we saw that this basically, that minimum now is just the probability of making a mistake between choosing two distributions, which we can say is minimized by this Neyman-Pearson test. So we're able to explicitly compute this. And that's how we got the S over 4 times the, and what we're computing is what's the error probability of this Neyman-Pearson test, which as we saw was, I'll call it P to the n, Q to the n. We picked two things that were a distance s apart, and that's the chain of events.
Will lower bound change according to the number of distributions we pick and how we pick?
Okay, so that's a good question. So right now, why am I picking two distributions? What's that?
For x places solution.
For what?
I mean, it's easier.
Well, it's easier, and then sometimes it's enough. We'll see when it is enough. So sometimes 2 points is enough, and you can do Lecombe's lemma. You're done. But for some problems, it doesn't give a tight enough bound. So we'll see that. I'm going to. How are we doing on time? Because I want to get the example in because I think this makes a lot more sense when you see a concrete example. But before I do that, are there any leftover questions? Okay, so let's actually see how this works in practice. The short answer to your question, by the way, is for computing something like the pointwise risk of estimating a function, Lecombe's lemma is enough. But when you want to compute something like the L2 risk, like you're doing in the homework, the integrated risk, Lecombe's lemma is not enough. When you have metrics that sum or average integrate things, two distributions isn't enough. Just to jump ahead a bit, that's going to be the answer. In fact, we're going to focus on, in this example, so this is example 8 on page 6. This example contains everything you need to know. If you don't get anything else out of these notes, this example really shows you everything, okay? We're going to do non-parametric regression. So I'm going to have y is equal to m of x plus epsilon. We'll keep everything as simple as we can. So we'll take, in fact, I'm going to take the xi's to have a uniform distribution. Remember, when you're doing minimax bounds, you get to pick out some distributions, right? You can pick a subset of the distributions. So even if the x's are allowed to have a general distribution, I might just choose the distribution where the xi's are uniform. We can always narrow the subset to get a lower bound. But at any rate, let's assume the xi has a uniform distribution. What's unknown here, to keep things even as simple as I can, I'm going to take the epsilons to be normal. So the only unknown quantity is the regression function. We're trying to estimate the regression function, okay? We need some assumption, and I'm going to take m to be in the class M of all Lipschitz regression functions. So remember what that is. It's m of y minus m of x. We're on the unit interval is less than, okay, for all x and y. So that's kind of the weakest smoothness assumption we've probably considered. We're just going to look at all regression functions m satisfying this Lipschitz condition. We're just doing one-dimensional non-parametric regression. And now I want to compute the minimax risk. Minimax risk of what? I'm going to focus on just a point-wise problem, not estimating the whole function, but how well can I estimate m at a particular point, just to make it, again, as simple as possible. So I'm interested in, let's suppose I want to know how well can I estimate m at 0. It doesn't have to be 0. Pick any point you want in the unit interval. I'll pick 0 because that's, it's arbitrary. So in other words, my theta, my parameter of interest, is the regression function at 0. All right. So I want to know, and let's suppose I use which loss function. I either used squared error or absolute error. I forget which one. I think I started with absolute error for some reason, but let's, yeah. So for some reason, I could have done this in squared error, but I'm defining my distance to be absolute. So in other words, you're going to give me an estimator at 0, and I have the truth. That's my loss function. And I want to bound the minimax risk. Okay? Let's do it. All we have to do, according to Lecombe's theorem, is pick any two distributions in this class. What are the distributions, though? The distributions all look like this. Every distribution in this class, there's really two random variables, p of x, y. And I can always factorize this as p of x times p of y given x. To make the problem easier, I've assumed p of x is uniform. So this is 1. And what is the distribution of y given x? Normal with mean m of x, right. So this is actually a normal with mean m of x. I hope I said that somewhere here. I did, yes. The density looks like y minus m of x. Right? It's just x is uniform, y given x is normal. And the mean is the regression function. All right, how am I going to construct two different distributions? Well, the distribution really only depends on the regression function. So I just have to pick two different regression functions. And here's the trick. You usually try to pick two very close regression functions, but they have to be in this class. They have to satisfy this Lipschitz constraint. And usually, if it's possible, people pick one of the functions to be the 0 function, because that's easy. So here are the two functions we're going to pick. I have to pick two regression functions. So the first one, hopefully I did pick 0. Yeah, so I'm going to call it m of 0 of x is 0. So there's my first regression function is, well, it's this. Now, I'm interested in estimating the regression function here. And remember, what is that thing I called s or delta? It's the distance between the parameter values. It's the distance, in other words, between m1 of 0 and m0 of 0. That's our parameter. So what I'm going to do is I want to make these functions as close as possible. I'm going to do something like this. That makes them different here. That makes the s not 0. But otherwise, I want to make them as hard to tell apart as possible. And why did I make it look like this? Well, because it has to be Lipschitz. And so, if I tried to do some other weird shape, it might not be Lipschitz. This is kind of the simplest Lipschitz function I can think of. That's close. And to make sure it's Lipschitz, in fact, here's the formula. So my m1 is just this piecewise linear guy. It's L, and I'm going to pick a number. I'm going to call this epsilon. There's kind of a free parameter here. I'm going to have to figure out exactly where to put this. So this function is L epsilon minus x for 0 between x and epsilon. And then it's 0 for x bigger than epsilon. I've now constructed two functions. They're as close together as possible in some intuitive sense, but they're different the parameter values are different. In fact, what is the difference? At 0, this is what? I guess it's L epsilon, right? So the distance here is L epsilon. L is given to us in the problem. There's a free parameter here, which is how far apart should I move this? That's going to be determined by that Kullback-Leibler requirement, that the KL distance be about 1 over n apart. This is really showing you how all these things are done, okay? So what I'm going to do is simply choose this epsilon. So what are the two, by the way, let's write down the two densities now. So P of 0 is phi of y. P of 1 is phi of y minus m1 of x, which is this function. I'm going to compute the KL distance and set this equal to 1 over n. That was what we had to do to make Lacombe's, well, log 2 over n. The constant's not so important. Right? So that's pretty easy to do. That's just now algebra. Part of the trick here is you also want to pick distributions or things that are tractable, that you can either compute things or at least bound them. So what is the KL distance here between P0 and P1? By definition, it's this. Hi. Okay. Well, you're welcome to stay if you want. It's a pretty exciting class today. And, you know, we're integrating over two things here. We're integrating over x, and then we're integrating over y, which is over the real line. And now everything simplifies because the way to think about this is, well, you know, I've kind of written it all out for you, but you compute the KL distance jointly. You can write as the KL distance of y given x averaged over x. Does that make sense? Y given x averaged over x. So I did that for you, and it ends up being the KL distance between a normal 0, 1 and a normal m1 of x given 1. For each x, in other words, for every x, we just have two normal distributions. And the KL distance between two normals with two different means, does anybody know what that is? If I have two normals, say mean mu1 and normal mean 2, has anybody ever computed the KL distance between these? It's essentially a distance between, it's mu1 minus mu2 squared over 2. You know, that's just by direct calculation. So this becomes the integral. Well, actually, these two things are the same after epsilon. So I only have to integrate up to epsilon. And the difference of the means is L squared over 2. Okay, so if I do this integral, you'll trust me. It's L squared epsilon cubed over 6. That's just algebra, though, right? And there's nothing deep happening there. I just stuck in my distribution, computed the distance, but I need this to be, to use that lemma, I need this to be something like, the log 2 is not so important, but 1 over n. And now what does that mean? I can solve for epsilon. That tells me how far apart I can make these functions and still keep them about 1 over n apart. And the answer is, epsilon ends up being some constant over n to the 1/3. And that means we're pretty much done because the distance is between these two things. According to Lacombe's lemma, once we've chosen those two distributions, it's just 1 over 16 times that distance, which is, well, there it is. It's n to the 1/3, some constant. So we've actually proved a fairly non-trivial result. Let's state our result. What have we done? We've looked at the inf over all estimators. We'll call it m hat of 0. All estimators of m hat at a particular point 0. Again, could be any point. The sup over all, well, it's really indexed by this class of regression functions. And the expected value of m hat of 0 minus m of 0 is bigger than or equal to some constant to the n to the 1/3. That's a lower bound. How do we know if it's tight? The answer is you can check. You know how to do these calculations. If I do a regression version of the histogram where I divide this up into bins, and if I choose the bin width right, you know now how to compute bias and the variance line. You'll see if you choose the bin width correctly, you get an estimator whose maximum risk is of the same order, 1 over n to the 1/3. So you'll get an estimator such that no matter what distribution you will use in this class, you can construct the histogram estimator and you will get it to also be, this means I'm leaving out constants. So we've got the lower bound is 1 over n to the 1/3. The upper bound is 1 over n to the 1/3. We have the minimax rate. The minimax rate for estimating a regression function, at least at a point, under the Lipschitz condition, is n to the 1/3. In fact, if we had done this in d dimensions, it would have been messier, but not so much, not really that much harder. You would have had to construct, like a tent-shaped function over here, which is 0 over most of the space, and has to be Lipschitz. It's a little bit geometrically more complicated, but it's exactly the same construction. You would get exactly this following rate. I mean, the calculations would get messier, but the whole process would be the same. You can see that d equals 1 gives us this special case. For some reason, I did this in absolute value. If we'd done the whole thing squared all along, of course, we would have gotten the squared rate. So I don't know why I did it in absolute value, but the square rate maybe would have looked more familiar. That's starting to look right. Like, does this look familiar now? This is like 2 beta over d plus 2 beta when beta is 1. How would I have done it over a smoother class, like a Sobolev class or something like that? The answer is the following. I would still take one function to be the 0 function. The other function, I would have taken a slightly smoother bump. You can create little bumps here. Okay, and I think we're going to do it in an example later on. See, this is where you use the smoothness class. Because I'm allowing smoother functions, I can make a little bump. I have to just check that it satisfies that it's twice differentiable or 3 times or whatever condition you're making. And you do the same trick. You have to make it as close as possible, make it 0 everywhere else, compute the KL distance. That will tell you how big you can grow this, and that will give you the rate. It's essentially the same calculation. And what happens is that that's where this is going to come from. We got beta equals 1 precisely because we were forced to use a function like this. Okay, and you'll get different rates if you're allowed to use different types, shapes of bumps. which we'll have examples of that later. But yeah,
You only do this for 1 point at 0. What if we don't restrict to only 1 point?
right. So if all I care about was estimating at a single point, like if I want to ask the question, how accurately can I estimate a single point, we're done. Lacombe's method works. But suppose I'm interested in something like this. My distance function. And for those of you who asked about this in the homework, remember that this is not, the randomness isn't in x. The randomness is in m hat. It's a function of the training data. The expected value when we take the risk is the fact that this depends on all of the training data. Anyway, when we do this, it's going to turn out Lacombe's lemma won't cut it. You can try doing it, but you'll get a very bad lower bound. It won't match the upper bound. This is why on Thursday we're going to talk about the next step up, which is to use one of the more advanced methods, Fano's inequality or Sibikov's inequality, which is really, but I want to emphasize, the basic skeleton of what we've done is going to be exactly the same. The only difference is 2 distributions isn't enough. We're going to have to choose a larger set of distributions. But really, I want to pause here because all of that now is sort of mathematical mayonnaise. The whole conceptual framework is already spelled out for you. Everything we did today is sort of the conceptual framework for doing this minimax stuff, which is to write down the minimax risk, reduce it to a finite problem, and solve that finite problem. What's the probability? Once you have a finite problem, it's sort of what's the probability of making a mistake, of choosing the wrong thing? And that's really picking distributions sort of as spaced out enough so that the term out front is not 0, but close enough together so that they're hard to test apart if you were doing a testing problem. And so we got, again, something like s over 2 or s over 4 times the probability of making an error. That's kind of the essence there of Lacombe's method. And for Fano's method, it's going to be the same thing. We're just going to have n distributions here instead of 2 distributions. And this example I just did, again, is really emblematic of how all of these problems are solved. Sometimes you have to be, it might be difficult to try to choose this set of distributions. I don't want to give you the impression it's always easy, right? There's a reason why people write 40-page papers about what is the minimax risk for this problem. It's because it can be hard, but the basic framework is always kind of the same. Okay, are there any questions?
What if on different dimensions we have different smoothness?
What if, sorry?
On different dimensions we have different smoothness.
Oh, what if you have a smoothness that was changing over x?
Yeah.
That's a much harder problem. So there's something called, which we won't probably talk about, it's called adaptive minimaxity, which is, can you have a minimax estimator which instead of assuming it has a certain degree of smoothness like we're doing here, adapts to the degree of smoothness? And that's a much harder problem. And so we won't deal with that. But that's a doable problem, but it's more difficult. Yeah. Any other questions?
I'm not clear about how this probability becomes y the first one.
That one?
Yeah.
Oh, because we have x is uniform. Y given x is normal, centered at the regression function with variance 1. And the density for a normal is just phi of y minus its mean. This is just the standard normal density. Sorry, this is the standard normal density, yeah. Guess I should have defined that. Go through that example again because, like I say, if you understand that example, you understand it. It's everything after that. It's just extra stuff. I mean, it's important, but that's the core.
You started the lecture by talking about the upper bound and then the lower bound. So the upper bound side, we have more.
Well, the upper bound we get by picking our favorite estimator and hoping that it works. And in this example, we use the histogram regression estimator. And you just compute the bias and variance. You minimize that over all choices of bin width. And yay, it came out to n to the 1/3. But what if it hadn't? Then we have a problem. This is something that happens in real life, is people pick an estimator, and they get a rate. They do one of these inequalities, and they get a rate for the lower bound, and they don't match. And then you start scratching your head and going, my lower bound, maybe I didn't pick the right set of distributions. The upper bound, I didn't pick the right estimator. Sometimes it just works out, and sometimes you spend years trying to find which one's not tight, the upper bound or the lower bound. Sometimes they're never solved. So it can vary from you get lucky to you get very unlucky. But there's sort of an art to this, I guess you might say, right?
If I use another regression such as kernel regression, I will get the same rate.
No, so kernel regression would be the right thing to use if I had chosen a different smoothness class. If I had assumed two bounded derivatives, then what we would have gotten at the end of this is 1 over n in square root to the 4/5. And the lower bound would have involved choosing a bubble like this, and the upper bound would be using the kernel estimator. Okay, so just look that over again, because I know it's a lot to take in, and we'll do a little bit more of that on Thursday, and then we'll move on to another topic. Remember that the midterm, because of the ML Open House, has been delayed. That's changed on the course schedule. Okay.